We are very lucky to have Dr. Jake Shreckhise join us today. Dr. Shreckhise earned his PhD in horticulture from Virginia Tech, where his research examined phosphorus requirements of container-grown woody ornamentals and how growing media amendments affect phosphorus chemistry and availability. He then completed a postdoc with the USDA ARS Application Technology Research Unit in Worcester, Ohio, where he directed his focus on using ferrous sulfate to modify nursery substrates for improved nutrient retention. Currently, Jake is a USDA ARS research horticulturist at the National Arboretum satellite worksite in McMinnville, Tennessee. In addition to developing new best management practices that mitigate nutrient runoff from container nurseries, his program focuses on identifying water and nutrient-efficient selections of underused North American native tree and shrub species. Again, we're very fortunate to have Dr. Shreckhise join us today. And with that, please give a warm welcome to Dr. Jake Shreckhise.
Thank you, Craven. Let me go ahead and share my screen. All right, how does that look? Perfect. Yeah, well, thanks so much for the introduction and for the invitation. I'm so glad to be here. Happy to share some of this research with you guys. As Craven said, the presentation is on is titled "Ironing Out Phosphorus: Helping Nursery Plants Hold Their Pee." But I was asked to first give a brief overview on how research is a part of the U.S. National Arboretum and its influence on the National Arboretum's mission. So let's start with that. Again, this is just going to be very brief, but so this is the mission of the U.S. National Arboretum, and as you can see here in gold, research, it really is a kind of a keystone component of the mission. So the U.S. National Arboretum enhances economic, environmental, and aesthetic value of ornamental landscape plants. And this is through long-term multidisciplinary research, conservation of genetic resources, and of course the interpretive gardens and exhibits. And so, yeah, that middle component there is what the Floral and Nursery Plants Research Unit does. So the Floral and Nursery Plants Research Unit conducts broad-based multidisciplinary research for the floral and nursery industries. And just a few facts and figures here. We have 12 scientists total, 28 permanent employees, and then a handful of temporary employees, including some postdocs, visiting scholars, summer interns, and then we have 3 locations. Our research is located in 3 locations: Forest, DC, then Beltsville, Maryland, and then where I am in McMinnville, Tennessee. So a few more facts and figures. So researchers published 108 scientific papers or book chapters and 143 abstracts or talks in the past 3 years. Released 17 new cultivars in the past 15 years. These are just a few that actually came out of McMinnville: Ruby Slippers, Oak Leaf Hydrangea, and more recently the Sunglow Comet Witch Hazel. And we have formal collaborations with national and international partners, including many universities. In fact, we're in McMinnville, we're co-located with Tennessee State University. So we do a lot of collaboration with them. So our research areas and scientists, we have Dr. Todd Roundsville and Kevin Conrad. They lead the Woody Landscape Plant Germplasm team and are in charge of curating and broadening an already really extensive collection of woody plant genetic material. And it's to preserve the genetic diversity of woody landscape plants and support current and future breeding efforts. We also have taxonomy team, ornamental plants, led by Harlan Sabota, who actually recently gave a FONA talk, a digging in talk. He's responsible for preserving, managing, and curating the National Arboretum's herbarium and National Seed Herbarium, and oversees the collection's digitization efforts. And FMPRU has 3 research plant pathologists, Drs. Hammond, Wong, and Jordan, who conduct research involved in detecting, characterizing, and controlling pathogens of ornamental plants. Drs. Hammond and Jordan are really the authorities on viral diseases and woody ornamentals. And Dr. Hong's expertise is in bacterial diseases. The turfgrass genetics team consists of Dr. Warnke and Barnaby. They use some state-of-the-art techniques to identify genes that are responsible for abiotic and biotic stress resistance in turfgrass species. And then finally, Drs. Duan, Gauker, Puller, Alexander, and I conduct basic and applied research to develop superior nursery plants, like blight-resistant boxwoods or cold-hardy crepe myrtles, among numerous other examples, of course. And then improved production technologies. And that's actually exactly what I'm going to be talking to you today about. All right. So first, just a little background information. I'm not sure how familiar everyone is with the nursery industry. So let's start off with a little bit of background information. So according to the 2019 census of horticultural specialties, nursery stock production is about a $4.5 billion industry. And among horticultural crop categories, like those listed here on the left side of the screen, nursery stock production is really the #1 sector in terms of value sales, representing about 1/3 of all specialty crop sales. Now, within the nursery stock sector, a little bit over 2/3 of the total sales volume was actually from stock grown in containers. So why do nurseries grow in containers instead of directly in the ground? Well, there's lots of reasons. There's also some challenges to it. Just going to highlight a few of the advantages. One is that in general, container production does offer a greater economic return per acre. That's due to greater number of plants you can grow per acre compared to field production, and their shorter production cycle. You can actually turn over a container crop from propagation to a saleable crop, especially in faster growing species, in a single growing season. And then also in like a field production, you don't need high quality fertile soil in container-based production. So paired with that, soil substrates used to grow these plants in containers are highly customizable. So growers can really formulate a root medium that meets the needs, like specific needs of the plant, which is why you could have an azalea, which has a very low pH requirement, and a boxwood, which is higher pH requirement, growing all in the same zone, right next to each other. And probably the biggest advantage of container-based production is it allows for year-round sales. In field production, you're really limited to digging plants when those plants are dormant, mostly kind of in the winter or early spring. Whereas with container-based plants, you overwinter them in an overwintering house, and you can essentially sell them year-round. Now, container-based production is really made possible by soilless substrates that I mentioned before. Soilless substrates, same thing as potting media. And really, the biggest difference between field soils and these soilless substrates is that soilless substrates have a much higher total porosity. And this high porosity really allows for a high water holding capacity, but with sufficient aeration, And then they also must be, these soilless substrates must be physically stable. If those components start breaking down, you start losing your airspace, your roots can't respire. It's no good for growing plants in containers. So they must be physically stable. Typically, they're really high in lignin, which slowly to decompose. And then finally, they must be, of course, free of pathogens and phytotoxic chemicals. And most of these soilless substrates already are free of pathogens without needing pasteurization. Now, for the past few decades, pine bark has really been the substrate of choice for nurseries in the eastern US. Obviously, one of the biggest reasons why is plants consistently grow well in it. But it's also really inexpensive relative to like a peat-based growing medium. It's about 40% cheaper, which is a big deal when you consider just how much of that substrate you need to fill these huge 15-gallon pots that you see in the background photo. But one issue with a lot of these potting media is they're inherently low in nutrients, and that goes for pine bark as well. So, it's absolutely essential to fertilize if you want a saleable crop. Now, one of those, of course, essential nutrients that pine bark is inherently low in is phosphorus. Phosphorus, it's the 15th element on the periodic table. We're not giving plants what you use in matches, of course. That's elemental phosphorus. What plants can take up is called phosphate, which is a negatively charged nutrient ion. But phosphorus is essential to plants and animals. It's the P in ATP. The basic unit of energy, and it's also an essential component of a lot of cell membranes. Of course, phosphorus has many other uses, but if you look at a fertilizer bag, you'll always see that there's going to be a 3-number code. And this example in the top right corner, 18612. Well, that 6 is always, that second number is always going to be referring to your phosphorus in the form of P2O5 diphosphorus pentoxide. Now, when plants don't get enough phosphorus, if you have any background in like plant nutrition, the photo that they always show is a corn plant, and it has these purpling leaves, and unfortunately, a lot of times these textbooks will say, phosphorus deficiency can be identified by purpling of leaves, and a lot of agronomic crops, yes, that is the case, but in this diverse landscape of woody plants that we grow in nurseries, oh gosh, phosphorus deficiency manifests in a myriad of ways. So big leaf hydrangea does get that purpling of leaves, but really the first symptom you notice is stunted growth, as you can see in that the bottom left hand corner picture. But like in fig, it's totally different. Interveinal necrosis, so death of the cells in between the veins of the leaves. Now in panicle hydrangea, same genus, different species as the big leaf hydrangea. The first thing you notice, of course, is reduced growth, but reduced leaf size and general fluorosis. We've done studies and never actually seen purpling of the leaves in panicle hydrangea due to phosphorus deficiency. Evergreen azalea is another one we've looked at, and that typically phosphorus deficiency typically manifests as leaf tip necrosis. Now, one of the essential functions of we're kind of going to kind of combining these ideas of phosphorus and pine bark now. One of the essential functions of any growing medium is to serve as a reservoir for plant nutrients. So since many nutrients are absorbed as positive or negatively charged ions, like you see here in that diagram on the left, the capacity of a growing medium to serve as a nutrient reservoir is largely defined by its charge properties. Well, it turns out bark, pine bark, as well as most organic matter, is negatively charged, as a net negative charge. And if you think about like a magnet, the same rules apply. So like charges repel, opposite charges attract. Well, these nutrient cations that are listed on the far left in red, they hold on to the bark pretty efficiently. All right, you don't have many issues of these nutrient cations leaching out of the bottom of the containers, but nutrients like your phosphate and nitrate also have a negative charge. So So when you apply your fertilizers, you know, those negatively charged nutrients will just leach right out of the bottom because the bark doesn't have a capacity for uptaking a negatively charged particle. Okay, so if the bark doesn't have an absorption capacity or a retention capacity, all right, well, that means that we need a constant source of soluble phosphorus in the container, right? Constantly releasing phosphorus, because otherwise, you know, if you don't, then what you do apply is just going to run right out of the bottom of the container. Because another hallmark of containerized production is the amount of irrigation required. You think about that root ball only has a very limited volume to extract water. All right, so frequent irrigation, definitely every day, normally multiple times a day during the hottest months of the summer. So the combination of applying a constant source of soluble phosphorus and the need for frequent irrigation is why much of the applied phosphorus leaches right from the containers. But how much? You know, is this 5%, 10%? Well, we did a study a few years ago to see exactly how much phosphorus does leach when you use, you know, a typical controlled release fertilizer that's typically used in the industry. And what we found is that up to 65% of the phosphorus that we applied ran right out of the bottom of the container. It was never used by the plant. From a grower standpoint, that's money down the drain. Okay. Only about 8 to 13% of the phosphorus we applied was taken up by the plant. Now, phosphorus that leaches from these containers is then subject to surface runoff, whether in a retention basin on site or even or worse downstream in surface waters. You know, excess phosphorus is one of the leading causes of these toxic algae blooms. In freshwater lakes and streams alone, these algae blooms cost the U.S., and this is a conservative estimate, of about $2.2 billion per year, and that was from a study back in 2009. So probably much higher now. These costs were associated with like losses in value due to recreational water usage or waterfront real estate, or spending on recovery of threatened and endangered species. Now, this also has regulatory implications for not just agriculture, but also the nursery industry. In Maryland, in particular, they have one of the most stringent policies. That's the Water Quality Improvement Act of 1998. It requires mandatory nutrient management plans be developed by any agricultural operation grossing over 2,500 per year, which is basically every single agricultural operation, to implement these management plans and then track annual fertilizer applications. Now, more recently in Florida, the governor passed Senate Bill 712, which is the Clean Waterways Act. That requires growers to submit records of their nitrogen and phosphorus applications. And then this is directly from the bill. We don't know exactly what this means right now, but growers not in compliance may be reported to the Florida Department of Environmental Protection for, quote, regulatory action. I've even spoken to some extension agents in Florida about what that means, and they weren't really sure yet either, but they said that they didn't really want to find out. So what we're talking about today, and please forgive me for this little pun, but how to keep pea in the pot. So there are essentially three systems that affect phosphorus mobility in soil and substrate. You've got the fertilizer, right? Which is your source of phosphorus. You have the substrate itself, which is the medium through which your nutrients travel and interact. And then the irrigation, which is the carrier of all your nutrients. So today I'm going to first touch on briefly some of my research on optimizing phosphorus fertilization that I conducted before I joined the National Arboretum. And then I'll of course discuss my latest research on how growers can modify their pine bark potting media to improve phosphorus retention. All right, so starting with how much how much phosphorus do woody nursery crops really need? And this was I guess a component of my graduate work even. So again, let's briefly just touch on this, and then we'll get to this more recent research here at the National Arboretum. So this is a typical plant growth curve in response to increasing nutrient supply. It could be nitrogen, phosphorus, potassium. Doesn't really matter, but any limiting nutrient in the root zone. Initially, as your nutrient supply increases, you have a pretty dramatic and rapid increase in growth. Eventually, you continue to add that particular nutrient, and you don't get a corresponding response in growth. That's the adequate zone. And then way down the line, especially in the case of phosphorus, you get some nutrient toxicity. And this is not to scale, I would say. That adequate zone is really broad. It takes a whole lot of phosphorus and a lot of nutrients, really, a lot of your macronutrients, before you ever get toxicity symptoms. So the goal of my research was really, it was to increase your fertilizer efficiency. And the way you do that is to shift your nutrient applications within that adequate zone from the right to the left. The optimal nutrient level would be right on the cusp of deficiency and sufficiency, deficiency and adequate. All right, so we conducted 3 studies. We looked at both liquid and controlled release fertilizers, ranging from very low, like deficient levels of phosphorus, to sufficient. We assessed 9 commercially important nursery crop taxa representing a variety of nutrient needs, and then we replicated these studies in 2 different Virginia ecoregions. I'm not going to read these off one by one, but again, this is just a list of all the taxa or species that will be evaluated. Again, ones we were looking at really were the ones that were most of these are shrub species, and all are very economically important to the industry. Okay, so just a highlight of some of our major findings. One is that phosphorus requirements are species specific, right? This is kind of a duh moment, you realize, but there are some implications to this. So phosphorus requirements are species specific. So for example, in Helera holly, in one particular study, like in Helera holly, the minimum phosphorus concentration required to maximize growth was 1 part per million. And plants like azalea or panicle hydrangea, they needed between 4 and 6 parts per million. That might not seem like much, but that's up to a 50, 60, 70% reduction in phosphorus right now, right here. But more importantly, the current best management practice recommendation for phosphorus fertilization of nursery crops, really exceed plant needs, because the recommendation is between 10 and 15 parts per million. So, you could potentially reduce your phosphorus fertilization even if you're following the best management practices. We found that growers could reduce their phosphorus fertilization by 40 to 80% in liquid fertilizer, or 33 to 50% in controlled release fertilizers. And if anybody has any questions on that research, I know that was quick, then feel free to ask me after this presentation. We'll go into more detail. So, changing gears to increasing phosphorus retention by modifying the potting medium. Now, reducing unnecessarily high phosphorus fertilization is really a great start to keeping phosphorus in the pot. But much of the eastern U.S. is prone to heavy rainfall events during the growing season, and while there's less phosphorus in the container, the phosphorus that is there is still easily leachable. We haven't really changed the fact that pine bark is negatively charged, phosphorus is negatively charged. the pine bark is not going to hold on to phosphorus. So since I joined the National Arboretum, I've been researching a way to engineer the substrate to better hold phosphorus. So let's put this in context a little bit. In container production, we have a unique advantage in managing nutrient runoff, that I think that we're not really leveraging. So in row crop production, like you see on the left, we don't really have much of a choice in how we mitigate runoff or how we apply our fertilizers. The fertilizers are being applied directly to the soil, right? Now, whereas in containerized production, there's practically an impermeable barrier between the fertilizers that we apply for our crop and the rest of the environment. So essentially, all we have to do is keep the phosphorus from leaving those bottom few drainage holes in the bottom of the pot. And so for the past 3 years, I've been looking at We've been investigating amending the pine bark substrate with ferrous sulfate. And so what happens is the positively charged iron, from which can act as a bridge between the negatively charged functional groups in the substrate and the negatively charged phosphate ion. And what we found in just some preliminary laboratory studies is that when you add ferrous sulfate to that pine bark, you can more than quadruple the phosphorus retention capacity of that bark. But why ferrous sulfate? It's a good question. So ferrous sulfate is a common ingredient in many micronutrient fertilizers. It's a soluble iron salt because of just iron and sulfate. It is relatively inexpensive given the amount that you would need to retain phosphorus. A 50-pound bag costs about $20, and that's before bulk pricing. That's the price that I could find if we wanted to buy it. It does dissolve rapidly. Like I said, it's a soluble iron salt, and because it dissolves, it doesn't affect those essential substrate physical properties that I went over at the beginning of the presentation. This is really key, and this is really the difference between using something like ferrous sulfate compared to using some kind of like iron oxide or some other type of like phosphorus retaining mineral that isn't soluble. Because what happens is when you add those like a clay, which has been looked at in container production, but what you find is when you add some other type of insoluble clay, something, that clay ends up filling in the pores in the substrate and reduces your total aeration. And after it rapidly dissolves, another advantage of using something like an iron salt is the ferrous iron binds very quickly within minutes to organic matter, including pine bark. And it also holds on very strongly. So we wouldn't have to, hopefully when we looked at this, but we wouldn't have to worry about, iron and phosphorus leaching later in the growing season. So research objectives, so we back up. I'm going to share with you the most recent research, but we've conducted over the past 3 years, probably 10 to 12 studies looking at various variables related to incorporating relatively high rates of iron sulfate into a pine bark based medium and basically just seeing what happens. This last study is kind of a culmination of all the other studies or results from all the other studies. And what we were looking at was the effect of ferrous sulfate incorporation rate. Look at 2 different rates. And then the location of the ferrous sulfate amended bark in the container on phosphorus leaching and shoot and root growth quality. Let me explain here. Well, first of all, the plants that we used for this particular study, we used 5 different plants. I did work for the Arboretum at this point, but I was replicating a study that I conducted during my postdoc. I would have otherwise used a few more National Arboretum plants if Richard's listening in. But we do have a little cameo here. We did use 3A Green Giant, which is a USNA release. But anyway, again, the purpose of these selections these are all very economically important plants that have been shown before to have a range of nutrient demands. Okay, so the substrate treatments that I mentioned before. So we have rooted cuttings of all those 5 different plant species, and they were transplanted in 2-gallon containers containing one of 4 substrate treatments. So one was our control, which had no ferrous sulfate. Then we had a treatment with 5 pounds per cubic yard. So we're going to call it the high rate of ferrous sulfate amended pine bark, but only in the lower half of the container profile. So kind of serving as like a phosphorus filter, right? But being further away from the roots of the liners, at least initially. And then half the ferrous sulfate rate, but incorporated throughout the substrate profile. So we're going to call that the half rate, 2.5 pounds per cubic yard, or that high rate of iron sulfate, but amended throughout the container. Okay, so just wanted to point out that the second treatment has the same total amount of iron in it. These pots have the same total amount of iron in them as the third treatment. All right, this fourth treatment has twice the amount of iron as either of these other treatments, right? Because we're either doubling the volume or doubling or having the ferrous sulfate rate. So that'll be important later. Okay, our cultural practices, basically what we're trying to do is simulate nursery conditions and practices. We use a very typically used control release fertilizer, a 16611 plus micros. So even the control substrate did get supplemental iron from the control release fertilizer. We used the labeled medium rate. These were overhead irrigated with sprinkler irrigation. We had 10 replicants per treatment, and we grew these plants for 13 weeks, which was the point at which our pre-mid maples were we considered to be saleable, either needed to be sold or bumped up to a larger container. So before the first irrigation event, all the autumn blaze maples were nested inside these plastic mesh baskets that you see here, these basket lids, which were then secured to 5-gallon buckets. And then we had these plastic skirts that were taped around the outside of the pots and draped over the buckets to prevent any irrigation or rainwater from falling directly into the buckets without passing through the substrate. And I know this might look very simple, but these buckets, leachate collection systems were actually pretty tedious to manufacture. And so that allowed us to collect all the leachate over the course of the 13-week experiments. We sampled once per week. We weighed it to kind of approximate the volume leached, and then of course we later analyzed that leachate for phosphorus. At the end of the study, we took some foliar nutrient samples to look at the phosphorus concentrations in the leaves. We assessed shoot dry weight as a measure of shoot growth and root dry weight as a measure of root growth. We also measured for the pre-mid maples, or the autumn blaze maples. We also measured the caliper and the height. Okay, so results. What this graph shows is the cumulative amount of phosphorus leached per container per week over time. And that's just the only plant taxa that we actually collected all the leachate was that autumn blaze maple. I failed to mention this in the previous slide, but collecting the leachate from all 5 of the plant species that we use just would not have been economical or time efficient given the staff we had. So we did a very in-depth look at at leaching from the autumn blaze maple. So this is again the cumulative amount of phosphorus leached per container per week over the course of the study. Each line represents of course a different treatment. Now, 6 weeks into the study, which is actually can be a production cycle for some herbaceous crops in greenhouses, but 6 weeks in, we saw just tremendous reductions in phosphorus leaching from all 3 of those ferrous sulfate treatments. We saw a 72 to 87% reduction in phosphorus leaching compared to the control. By the end of the study, it did kind of depend on the treatment. That the treatment that had the lower ferrous sulfate rate, but amended throughout the container profile, the total amount of phosphorus that leached from those containers was about 25% lower than what leached from the control. Now, the 2 treatments with the higher ferrous sulfate rate, there was no significant difference in those 2 treatments, the red and the purple lines. And we saw a tremendous reduction of a 51 to 55% reduction in phosphorus leaching relative to the control. But what's really interesting is, remember what I said before when I was describing those treatments, that purple line, that high rate of ferrous sulfate throughout the profile, that has twice the amount of iron in the container, so per container, than the red line, right? Which is that, the same high rate, but just in the bottom of the container. So what this tells us is that all of that phosphorus absorption is really happening just in the bottom of the container anyway. So this concept of like adding a filter layer, if the nursery is capable of doing that, should work really well, right? That would allow them to, reduce the total amount of ferrous sulfate they have in per container, by half. It's just whether or not they're set up to include a quote filter layer in the bottom and use two different medias in each container, which some nurseries have actually switched to doing, but not all operations are set up that way. All right, now this is basically the same information, but I just wanted to point out something. So when we looked at the data at the end of the study, we saw these really interesting peaks in phosphorus leaching every few weeks. And when we overlay that with rainfall, I mean, it is directly correlated with those peaks in phosphorus leaching is directly correlated with the amount of rainfall. And so what we found is that those rainy weeks where we got more than 3 centimeters of rain per week which represented less than half of the total number of samplings we did, but accounted for 89% of all the leached phosphorus from the control. But those rainy weeks were when the ferrous sulfate was most effective as well. As you can see throughout the study, of course, as those adsorption sites become more and more saturated with phosphorus over time, the ferrous sulfate becomes less and less effective. But even towards the end of the study, you can see at week 11 here, that highest rate of ferrous sulfate throughout the container profile was still very effective at reducing phosphorus leaching. Shoot and root growth for 4 of the 5 species was totally unaffected by any of the treatments. We did see something kind of interesting with Freeman maple. The control did tend to have slightly higher shoot and root dry mass. And when we looked into the foliar nutrient concentrations, we noticed a very slight, a few hundredths of a decimal difference in the phosphorus concentration in the leaves, with a slightly lower phosphorus concentration in the treatments that did have ferrous sulfate. So what that would indicate is that, it could be possible with a very fast growing tree species like Freeman maple, that eventually the ferrous sulfate could limit phosphorus availability. But When we repeated the study, we didn't see any difference. Well, we certainly didn't see a reduction in growth. We certainly didn't see a reduction in growth from the ferrous sulfate treatments in Freeman maple, and actually, in the treatment with the treatment with the high rate in just the bottom layer, for whatever reason, those plants had higher shoot dry weight than all the other treatments, including control. So we're not really sure what the deal is with this inconsistency, but all the other treatment responses were consistent across the two studies. When we looked at caliper and height, this is the study that I've been talking about. The caliper and height of that Freeman maple, there were no noticeable difference, or there were no differences in caliper and height, and there were no noticeable differences in root health across all the treatments. Also notice how root bound those plants were. I mean, it's no wonder that if there's any reduction in phosphorus availability at all from the ferrous sulfate, it would probably show up, given how massive those root balls are. Just a little illustration of what happens when the roots reach that ferrous sulfate amended layer. It's convenient, the ferrous sulfate actually stains the bark black for whatever reason. We haven't noticed any staining from the gravel under the pots, but it does tend to stain the bark black. But anyway, what this is just showing is that the roots grow right on through that ferrous sulfate amended layer with no problem here. So I've mentioned that we've conducted probably about 12 different studies. I just wanted to show that these weren't the only 5 taxa that we've looked at. We've looked at a whole bunch of different economically important nursery species, and of all these species, the only species, or the only taxa that was negatively affected by that ferrous sulfate was the autumn blaze maple in that one study. Okay, coming up on 40 minutes, so just a few conclusions here. So 2.5 to 5 pounds per cubic yard of ferrous sulfate can greatly reduce phosphorus leaching, and that corresponds to the rate of ferrous sulfate. And we also found that concentrating the ferrous sulfate in the bottom of the container could be a very effective way to kind of filter your phosphorus before it leaves the container, if the nursery is set up that way. So these reductions would probably be even more with a lower phosphorus fertilizer, so that that iron charged bark isn't being saturated quite as quickly, and it's effective even during heavy rainfall, which is really probably one of the most key findings of this research, because all the other best management practices designed to reduce nutrient leaching, they can't really protect against heavy rainfall events, to my knowledge. So effective against heavy rainfall events, with the exception of maple, no major positive or negative effects on crop growth. So really what it all comes down to is cost. So, I mentioned before, a 50-pound bag of ferrous sulfate before bulk pricing is about $20. So do the calculations, what that comes out to is about 3 cents per 3-gallon pot, or a penny per gallon. And that's if you were to incorporate throughout the container profile. If you were to incorporate just in the bottom of the container, that's going to be technically 1.5 pennies per 3-gallon pot, right? So some future research, we're still looking at combining low phosphorus fertilizers with iron church substrate. We actually have a project underway in Worcester looking at that specifically. We're also looking at using ferrous sulfate amended substrates in greenhouse production to see if we can kind of expand the utility of this substrate, this phosphorus absorbing substrate, to the greenhouse industry. And that also involves looking at rather than just incorporating pine bark with ferrous sulfate, but also the greenhouse substrates like peat, cocoa coir, and wood fiber. So that wraps up the presentation. Thank you all for your attention, and I would be more than happy to answer questions.
Well, thank you very much, Jake. Appreciate the presentation. I'm going to check for questions here. We have one question. How has the nursery industry reacted to this research? Have growers started to incorporate ferrous sulfate into their operations?
Yeah, I have one. So I presented this research in at Southern Region IPPS, International Plant Propagator Society. And I honestly, I really need to follow up, but there was about 3 growers, mostly that came up to me after the talk saying that they wanted more information on how to actually implement this in their nursery specifically. One was in Florida. Of course, you know, basically they're in the states where nutrient regulations are the most harsh. So one Florida grower was extremely interested in using this because I couldn't get the details right, but some downstream homeowners association they were on this nursery's back about nutrient leaching and algae blooms and whatnot, and so, you know, they're wanting to implement some nutrient reducing pest management practices to kind of get them off their back. And there's another nursery, actually the other nursery was in Florida, another one in Florida. And honestly, I can't remember where the other nursery was from. But anyway, so I still need to follow up with them. That was that presentation was the first time I gave this to a very broad audience of growers. So the short answer to this is I will find out soon.
Okay. Next question is, where does ferrous sulfate come from? Is it from a sustainable source?
Yeah. Oh, and I forgot to mention, back to that first question. What the industry that seems to be more interested in adopting the ferrous sulfate amended bark is actually the substrate manufacturers. I'm not going to mention their name because they haven't committed to this on paper, but we do have a very large substrate manufacturer in the U.S. that's very interested in offering ferrous sulfate amended pine bark products to their growers. So anyway, I meant to mention that really the substrate manufacturers may be more interested in adopting this than the growers. So where does ferrous sulfate come from? Ferrous sulfate is actually it's made by combining ferrous iron with sulfuric acid. Is it sustainable? It's made in such bulk right now for other industries that, you know, whether or not, I don't know that the sustainability of it, we would be using such a small market share of what's already being produced for like wastewater treatment, that I think the advantages of on sustainability that they would provide in terms of reducing phosphorus leaching would outweigh any kind of sustainability issues, if there are any, in terms of manufacturing ferrous sulfate. So it's available at most like farm supply stores. So ferrous sulfate's available at like these greenhouse mega stores, basically any of these distributors of greenhouse and nursery products. Stop.
You mentioned that the suppliers are more interested right now than the nurseries. What are in your mind, some options to get this out to the industry? And are there any patent opportunities for the Arboretum for the solution?
I don't want to talk too much about this right now, but yes, there might be some patent opportunities that just recently kind of manifested. That we're talking to one very large substrate company, and I'm basically waiting on details from them on how we want to proceed with this. In terms of getting out to the nursery industry, So nurseries, a lot of nurseries, a lot of the large container-based operations already have a substrate mixer. And so, they can mix this directly into the substrate themselves. Getting them to adopt this is going to be mostly just talking to growers. And like I said, I need to follow up with the growers that have expressed interest already, and making sure that they have very detailed we'll say very simple instructions on how to incorporate it into their bark mixes, and what rate to use, what species you might have issues with if you use a ferrous sulfate amended pine bark, if any. So I think that probably answers the question.
Okay. And then we're coming up on the top of the hour here, but any next steps or the future for this research that you'd like to share?
Yeah, something that's really interesting that we're doing in collaboration with Ohio State is, so there's some researchers looking at using phosphorus solubilizing bacteria in greenhouse production. And so they saw this ferrous sulfate amended bark research at a American Society of Hort Science presentation, and they're interested in incorporating the ferrous sulfate with like a very cheap form of phosphorus to essentially bind up all the phosphorus in their media, and then using these phosphorus solubilizing bacteria to make the substrate serve as like a slow release fertilizer. And we are in the beginning stages of the first study looking into this, and we'll see what happens. We'll also see the economics of all this, but that's up to the greenhouse team to kind of investigate. So, but kind of a unique application of this research.
All right. Well, Jake, thank you very much for joining us today, and I want to thank all the attendees for joining us as well. Another great edition of Digging In. Want to let everybody know, keep an eye out on the FONA website for other Digging In events. And remember, we've got the 5K coming up on June 3rd and the U.S. Navy Band concert on Sunday, June 11th. Again, thanks to everybody for joining us, and we hope to see you again next time. Again, one more thanks to Jake. Really appreciate the presentation today and the information you shared with us. Very, very kind of you.